Hello. So this lecture is going to be a little bit of a digression from the class lectures because you're not really going to be held responsible for this, but this is actually a really cool fact about conditional series, convergence series versus absolute convergence series, and it's actually sort of important. So I wanted to say a couple things about it. What I've got here in front of you is your classic conditionally converging series, the alternating harmonic series. Although it's the negative of the alternating harmonic series I was talking about before, but same thing works. It's still an alternating series that converges. And I've listed out the first couple terms. It converges to some number L. And we know by the alternating harmonic series test that L's going to be trapped between consecutive partial sums. So the first partial sum is 1. The second partial sum is 1 minus 1/2, which is 1/2. So L is somewhere between 1/2 and 1. In particular, it's bigger than 0. In fact, it can be shown, although we won't do that here, it can be shown that L is equal to ln of 2. But that's a digression. That's not really that important. Okay, it's just that it's L, and L is not 0. Not 0 is important. Okay, so let's multiply this thing by 1/2. So I'm going to call this equation 1. And equation 2, I'm going to get by multiplying everything by 1/2. So I'm going to get 1/2 minus 1/4 plus 1/6. Notice that I'm only getting even terms in the denominator when I do that. 1/8 plus 1/10. And I'm writing a whole bunch of them out because we're going to need them later. 1/12 plus 1/14 minus 1/16 plus 1/18 minus plus, so on down the road, and that's going to equal 1/2 L, which of course is not equal to L because L is not 0. And then in the third equation, well, the third equation is going to be exactly the first equation, the second equation, except I'm just going to add some zeros in there. So let's look at that. That's going to be, I'm going to add zeros where all the odd spaces were in equation 1. So 0 plus 1/2 plus 0 minus 1/4 plus 0 plus 1/6 plus 0 minus 1/8 plus 0, and so on. And of course, that's going to equal 1/2 L as well. So now let's look at this. I'm going to take equation 4. It's going to be 1 plus 2. So equation 4 is going to be 1 plus 2. Equation 1 plus equation 2. So what am I going to get there? Well, I lined it up so I've got terms. So I've got 1. The 1/2s cancel. I get plus 1/3 minus 1/2. The 1/4s come together, plus 1/5 plus 0. The 1/6 cancel, plus 1/7 minus, what happens when I add the 8s? I get 1/6. I get 1/4, right? Minus 1/8 minus 1/8 is minus 2/8, which is minus 1/4 plus 1/9. And let's see if we can figure out what's going on. So the odds are just coming, they're just going to be positive, right? All the odds are going to be positive. And every other even cancels out, but the next even is going to be the even that was canceled out, but negative, right? So the negative 1/2 and the positive 1/2 cancel out, but the negative 1/4 and the negative 1/4 add up to negative 1/2. So we get our negative 1/2 here, and we get our negative 1/4 here, and we're going to get 1/9 plus 1/11 minus 1/6, the next even here, right? Now we're going to have 1/13 plus 1/15 minus 1/8, the next even here, and so on down the road. Okay, and the thing is, well, when I add these L's, I get L plus 1/2 L, which is 3/2 L, which of course is not equal to L, right? Because L is not equal to 0. That's really worth pointing out. However, what you need to notice here is this is just a rearrangement of the alternating harmonic series. Exactly the same terms. All the negative evens show up. all of the positive odds show up. This is just a rearrangement of the alternating harmonic series. And it sums to something different. We get a different sum. The harmonic series sum to this thing L, which happens to be ln of 2, and this rearrangement sum to something completely different. We don't have the ability to just rearrange series in general. In fact, Riemann proved that, in fact, if a series converges conditionally, you can rearrange the series to get anything. So it's really sort of a weak convergence. It's really precarious. If you just tweak anything at all, you get something else it converges to. So that's sort of a surprising fact. But the thing that's nice about absolute convergence is, in fact, if you know it converges absolutely, it can be shown that you can rearrange things and treat them as they were just normal series, and you'll get the same sums, normal summations. With absolute convergence, the infinite sums behave just like finite sums do. And so that's going to come up from time to time in future lectures. Okay, good place to stop.